Straten, who's Associate Professor at the Institute of Radio Astronomy and Space Research at the Auckland University of Technology. And he's spoken to us before and was definitely a good friend of the Society. So thanks very much for coming along and just going to tell us about imaging, I guess it's magnetic fields in the galaxy, the local galaxy, or further afield.
On all scales.
Oh,
yeah.
Yeah. Okay, thanks.
Thanks, everyone, and thanks, Bill, for the invitation to speak. Also, thank you for coming this evening. I know it's foggy and rainy and cold. I'm going to talk about magnetic fields and a subject that's kind of close to my heart, polarization. I'm stepping a little bit out of my comfort zone and talking about polarization across the electromagnetic spectrum. I kind of focus on radio polarimetry in my own research, but I guess my main goal is to convince everybody that magnetic fields are really interesting and that polarization is also very interesting. So this is kind of a rough outline of the main topics. I'm going to spend a little bit of time along the way talking about the different types of astrophysical sources that have magnetic fields or generate polarized radiation from which we infer the presence of a magnetic field. So starting pretty much on the local scale, I mean, I'm not going to talk about fridge magnets and things like that, but magnetic fields are pretty much everywhere we look in the universe. Of course, the sun has its magnetic field, and the winding and twisting of its magnetic field leads to a lot of pent-up energy that occasionally gets released in the form of these coronal mass ejections. So basically, this is magnetic energy launching ionized particles. That's the sun, and that's the size of this coronal mass ejection. These are enormous eruptions of energy. If you think, 100 Earths can fit across the diameter of the sun, we're talking about a really big magnetic storm. Luckily, Earth's magnetic field protects us from such things. It deflects the ionized particles that are flying towards us at high speed, and very beautifully deflects those particles primarily towards the polar regions where they occasionally light up the upper atmosphere, causing gases to fluoresce. In our daily lives, magnetic fields are all around us. They're also around through the solar system. So Jupiter has aurora as well. This is a false color image of the aurora taken with the Hubble Space Telescope up at one of Jupiter's polar caps. We also now understand that magnetic fields play a vital role in the formation of planets. So when you have a swirling disk of gas and dust and charged particles around a protostar, the magnetic fields play an important role in confining and helping planetesimals to form out of that gas and dust. So looking outside of our solar system, we have amazing objects like pulsars, for example. These are neutron stars with very powerful magnetic fields, millions or billions or even hundreds of billions times stronger than what occurs naturally in our solar system. I think it's even 1,000,000 times stronger than the strongest magnetic field that has ever been produced in a lab here on Earth. And so coming out of the north and south poles of this magnetic field, it's like a cosmic particle accelerator. Yeah?
I read that there's some magnetars that it's close to the moon, they stick the iron into the blood.
It's close. Yeah, that's right. It would be like a really, really powerful MRI. Yeah, they're amazing. So you've got this particle accelerator that's sending out charged particles at close to the speed of light, and then those particles emit across the electromagnetic spectrum from radio up to gamma rays. On a much bigger scale, we have the supermassive black holes at the hearts of galaxies. They have accretion disks, so there's gas again and dust and ions swirling around these black holes. When you get ionized particles moving around at high speed, you can treat that like a current. So some sort of current forms in some sort of way, generating magnetic fields. And it's thought that these magnetic fields in the vicinity of the black hole are what launch these jets of gas these jets become larger than the galaxy itself. They launch particles out to huge distances away from the galaxy. Our Milky Way has a magnetic field. So this is a depiction of the Milky Way magnetic field determined from the Planck mission. So they looked at the polarization of the radiation emitted by dust, and they had to model this foreground, the galactic foreground, in order to accurately image the cosmic microwave background. You can also see when you take an image of the center of our galaxy in the far infrared light, you can also see these celestial dust grains that have been aligned along the magnetic field, and again, causing the light from that region to be polarized. So again, what's being shown here is the direction of the magnetic field as inferred from the linear polarization of the light coming from the galactic center. And some of you may have already seen this amazing photo. It's a montage of X-ray. So different energies of X-rays are represented using different colors here, and it's combined with an image of from the radio band taken with the Meerkat radio telescope in South Africa. And again, at X-rays and in radio, you're seeing a lot of high energy emission, but you're also seeing emission that comes from synchrotron motion of electrons, and I'll come back to that in a bit. But again, this is a lot of the activity that we're seeing here is thought to be driven by magnetic fields, these things that are called magnetic reconnection events, where huge amounts of magnetic energy are released in the form of launching particles at high speed. So we have magnetic fields on galactic scales, and then even when you have clusters of galaxies, so there's two galaxy clusters labeled here, Abell 0399 and Abell 0401. There's been recently a discovery made by the LOFAR team, so this is at really low radio frequencies of around 140 megahertz. This ridge of radio emission, which again is synchrotron emission that's emitted by these electrons that are moving at high speed as they circle around a magnetic field. So that contained radio emission is telling us that even on the scale between galaxy clusters, there's ionized gas and magnetic fields spanning over millions of light years in space. These fields are quite weak in comparison. They would be measured in micro-Gauss, so that would be about 1 million times weaker than the magnetic field of our sun, for example. So magnetic fields are everywhere. Everywhere we look, we see them. And the main way we detect them is by measuring the polarization of the light waves, or the electromagnetic radiation. So this is a classical picture of an electromagnetic plane wave. So we see here light propagating at the speed of light, slowed down, thankfully. The red arrows, you could think of them as the electric field oscillating kind of in a vertical plane, and the blue arrows, you could think of them as the magnetic field oscillating in a plane that's perpendicular to the electric field. And this is a classical picture that's been around since the late 1800s about how light propagates through a vacuum. If you're not happy with the animation, here's a frozen picture in time. Yes, this one is frozen in time. So what we're seeing here, the distance between crests of a wave would tell us about the wavelength of the light. So this would be a monochromatic wave. And really, we're talking about linearly polarized light when, for example, if the red line is the magnetic field in this picture, and the blue lines are the electric field oscillating up and down. So we would call that, if this was oriented as it is in the room, this would look like a vertically polarized light. You can have linear polarization of any orientation. You just rotate about the line of sight. You could rotate by 90 degrees and turn this vertically polarized light into horizontally polarized light. You can also have circular polarization where if we look at, there's a circle embedded in this image here with a kind of red cylinder flowing away from it. And if you just look at the behavior of the electric field vectors on that circle, they're just rotating around. With every period of the wave, the electric field does one complete circle. And so this is the definition of circular polarization. The helicity of this shape that we see, the corkscrew shape that's flowing through space here, it can be a right-handed corkscrew or a left-handed corkscrew, and that's what tells us, or those are the two types of circular polarization that you can have.
Does the direction of motion change if the corkscrew changes side?
No, for those two-handedness, yeah, that's right. The direction stays the same, but the spinning of the electric field can go either way. Yeah, yeah. There is definitely a relationship between the electric field, the magnetic field, and the direction of the light that's always fixed. Yeah, yeah. This is just that same picture frozen in space. It's kind of showing how you can think of circularly polarized radiation with that red corkscrew in space as a sum of linearly polarized states, the green wave here being like a horizontally polarized state, and the blue line here showing a vertically polarized state. So if you phase shift those two by 90 degrees, so one is a cosine and the other is a sine wave, then you get circularly polarized radiation. In general, light is elliptically polarized. So if you were to project, like if this little dot here is your line of sight going into the screen, and this XY, these XY axes represent where we're measuring the electric field. If we had a monochromatic wave, in general, that monochromatic wave would trace out an ellipse. And you can describe this ellipse in terms of its amplitude, which is like the major axis or even the semi-major axis of this ellipse. So always measuring the long end of the ellipse. And then the angle that this ellipse makes with respect to the x-axis is given by psi, that tells us the orientation of the ellipse. And then the axial ratio is given by the tangent of this angle chi here. So those three numbers can fully describe the polarization state of a monochromatic wave. So in general, how do we generate this polarized electromagnetic radiation in the first place? I think most of us are familiar with the use of polarized sunglasses, for example. After light reflects off of a surface like water, it becomes horizontally polarized. So if you wear glasses that preferentially allow vertically polarized light to come through, then they'll strongly dampen the horizontally polarized light and cut down on the glare. So this is just from an ad for polarized sunglasses. But here you can see the same image with vertically polarized lens in front of the camera, and that same image, we're now sensitive to all of the reflected glare off of the water without the polarizing filter in the way. So that's a simple example from here on Earth, but stars actually reflect polarized light. So in the binary system that has spica A and spica B, you can measure these two parameters. I'll come back to these parameters later. Q and U measure the linear polarization of the light, and we can see over one, here phase is talking about binary phase, so we're talking about one rotation of the binary system. You can see the polarization of the light in that system varying, and that's because each of the two stars is reflecting the light of the other star and polarizing that light.
It's not the emitted light, it's the reflected light.
Yeah, that's right. So the light from B reflecting off A and the light from A reflecting off B.
So the emitted light would be just randomly polarized, I guess?
Yeah, that's right. In general, if you just have a whole bunch of particles like a sun emitting light, then it'll be unpolarized on the point of emission. Yeah. From modeling these light curves, actually, they're able to describe the tidal distortion of one of those stars, so they can actually determine the shape of the stars, which is pretty amazing. You can also polarize light by scattering. So if you have sunlight coming in from the left here, hitting some molecule, so the sunlight is unpolarized. The electric field is dancing around in all directions, but it's always in a plane. The electric field is always in a plane perpendicular to the motion of the light. So that electric field causes some molecule in our atmosphere to bounce up and down and around. But if you look at that molecule from straight below it, you'll just see the molecule dancing around in a plane that's perpendicular to the direction of the motion of the light. So you'll see the electric field of the radiation coming off that particle to be polarized in that plane. In this case, let's call this the north-south plane, if you will. It depends on your viewing angle. So if you're looking at that same molecule from over here, you'll see a bit of circular motion, or you'll see motion in all directions. Here you see motion in only the one direction. Here it's partially polarized, and if you look at the molecule moving straight on in the direction of the source, you'll still see unpolarized light. So the degree of polarization depends on the angle that you're viewing. And this is pretty neat. I mean, ions and dust and gas in our galaxy interact with electromagnetic radiation from all the stars in our galaxy, so they can polarize the light. You can also have them acting as a Polaroid filter, so the preferential motion of these gas molecules when they're aligned along a magnetic field can selectively absorb some of the polarized light. And in this case, the alignment of the gas particles along the magnetic field, here we're looking at a small piece of the Milky Way along the plane. Here, even just the thermal radiation that's coming off of these particles is polarized because of the presence of a magnetic field. So now we're starting to talk about magnetic fields. Another way that we can see or detect the presence of magnetic fields, first of all, in the way the magnetic fields line up the particles and cause the light from those particles to be linearly polarized. But on its way to Earth, if that light passes through a plasma, so here this cylinder represents some volume of plasma, and here we have an electric field that starts out vertically polarized. And as it passes through this plasma, if that plasma has a magnetic field bathed, or if that plasma is bathed in a magnetic field, then the plane of the polarization will rotate as it passes through this material over some distance d. The magnetic field could be quite weak, but that, over stellar or interstellar distances, this effect can build up over and become quite large. So when we observe the radiation, we see that the angle has, or the plane of the linearly polarized light has rotated through some angle beta. So you can ask, well, how do we know it rotated? How do we know it didn't start out at that angle? This effect nicely varies with frequency. So if we look at different radio frequencies, for example, we can see this angle beta typically varies with the square of the wavelength of the radio waves that we're looking at, or light waves for that example, for that matter. So using this Faraday rotation effect, you can kind of do tomographic mapping of the magnetic field of our galaxy up. So that here you see the center of our galaxy, and then up here is us orbiting the sun. And what you see is a model of the positions of pulsars in our galaxy. So pulsars, these rotating neutron stars, they produce linearly polarized light, and we can measure the Faraday rotation of that light and then infer from that the direction of the magnetic field. And what you see here are mostly blue circles on this side. These are negative rotation measures. And what you see over here on this side are mostly positive rotation measures. So RM, this rotation measure, is basically telling us is the magnetic field pointing toward us or pointing away from us. So you can get rotation in both directions depending on the orientation of the magnetic field. And you can see at a large scale that there is kind of this structure where the magnetic field lines are either pointing towards us on this side and pointing away from us on the other side, or the other way around. I can't remember the direction off the top of my head. So Faraday rotation is one way to detect magnetic fields using the polarization of light. We can also see the presence of magnetic fields through something called the Zeeman effect. And what this is showing are spectral lines from Mercury. And what you see in, not quadrant, but whatever it is when you divide something by 3, what you see in this third is are the spectral lines when there's no magnetic field. And then in points B and C are 2 cases where the magnetic field is switched on and aligned in a certain direction. What the magnetic field does is splits each one of these spectral lines into a finer set of spectral lines. And we can observe that. So in an astrophysical context, again, we have some plasma bathed in a magnetic field. That plasma might be driven by some stimulated emission, like maser emission, and that maser is emitting spectral lines, and those spectral lines get split, and they get split into 2 oppositely polarized spectral lines. So the one becomes circularly polarized in one direction, and the other spectral line becomes circularly polarized in the other direction. And we can use this, we can measure this Zeeman splitting of spectral lines into oppositely polarized lines to map out the strength of the magnetic field at the point of emission of that radiation. This image here is being supplemented by some additional information about the linear polarization, which is represented by the yellow lines. So the Zeeman splitting effect is being shown in colors. It's telling us about the strength of the magnetic field at the point where the radiation originates. So Zeeman splitting can tell us about the strength of the magnetic field at the point of emission, and then Faraday rotation can tell us about the strength and orientation of the magnetic field between us and the point of emission of the radiation. So another way, so I talked a little bit about synchrotron radiation when I mentioned black holes, but basically if you have some magnetic field lines and electrons spiral around those magnetic field lines, those electrons will emit radiation as they spiral around, and that radiation will have a preferred direction of its electric field, so it produces linearly polarized light. And that's the effect that was used to produce this image of the supermassive black hole in a nearby galaxy. So this supermassive black hole is about 6.5 million times the mass of our sun. So it's a huge black hole. It's about 55 million light years away. We've all seen this donut image of the glowing gas, the accretion disk around the black hole. It's been recently supplemented by measuring the linear polarization of the light, and from that linear polarization, inferring the direction of the magnetic field lines that are embedded in that accretion disk. And again, this is adding more credence to this idea that magnetic fields are responsible for the jets that get launched by these supermassive black holes.
Was there any way to measure the strength of the magnetic field in that case? Or?
It's the degree of polarization is pretty weak, so there's quite a bit of scrambling of the signal, and I don't know if they can infer the strength of the magnetic field. Yeah, so far just the orientation is all I've seen. All right, so how do you actually measure the polarization of electromagnetic radiation? So the way astronomers and possibly also in many other fields measure polarization state is through something called the Stokes parameters. So if we go back to that picture of the polarization ellipse that was characterized by these 2 angles, those 2 angles become they're called spherical coordinates. So you can think of the psi as the longitude, and chi, or 2 times psi gives you the longitude, and 2 times chi gives you the latitude on the surface of some sphere. And the length of the vector in this space is given by the intensity of the light times the degree of polarization. So 100% unpolarized light, like that from the sun or any other thermal source, would just be here at the origin in this 3-dimensional space. And then 100% polarized light would be out on a sphere of, if we divided this whole thing by I, the intensity, then you would 100% polarized light would be out on the surface of that sphere. So Stokes parameters are kind of an abstract way of representing polarization state. I'll show you how they're measured in a moment. But basically, there's 4 of them. There's these 3 numbers here that represent this point in a 3-dimensional space. So we call them S1, S2, S3 in this diagram. S0 is the total intensity, which tells us about how bright the source is. So all 4 Stokes parameters have units of flux density or intensity or whatever we're using to measure the energy in the photons that we receive. Now, the way we measure the Stokes parameters is typically by making 6 sets of intensity measurements. So we take linearly polarized filter and orient it at, say, 0 degrees, like horizontally polarized light. And we make an image of whatever it is that we're trying to measure the polarization of. And then we rotate that filter by 90 degrees and measure the vertically polarized light. And taking the difference between those 2 intensities coming out of this filter tells us the first Stokes parameter, S1. And then we do it again with the same filter oriented at 45 degrees, measure the intensity, then orient it again at 135 degrees, take the differences between those 2 intensities, and we get S2. And then finally, we need to measure circular polarization. So chi equals 45 and chi equals minus 45 represent left-handed circular polarization and right-handed circular polarization. So with these, again, you take the difference, and that gives you S3. When those intensities are all equal, then all 3 of those numbers will equal 0, and that's what you get for unpolarized light. So it's just a little cartoon to help remember. What we have been calling S1, S2, S3 are more commonly called Stokes Q, U, and V. So Q is the difference between horizontally polarized and vertically polarized light, and U is the difference between linearly polarized light at 45 minus linearly polarized light at 135 degrees. And then Stokes V is the difference between left-handed circular and right-handed circular polarization. Yep?
How can you measure circular polarized light? Like, is there a filter or something that is?
Yeah. And that's perfect timing, because I got my information about how to measure optical polarization from I just read a couple of papers, one on the archive and one that you can get on NASA ADS. These kind of give a nice introduction to the equipment that's used for measuring polarization. But basically, to set up a polarimeter, you need 2 pieces of equipment. One, which is called the modulator. It changes the polarization state of the incoming radiation. And then another filter called an analyzer. So that a modulator, there's kind of 2 kinds. You can have a constant phase plate or a variable one. The variable ones are based on some pretty fancy electronics. They're typically optimized for a pretty narrow band, so you can't use them over the whole optical spectrum. It's much more common to get these constant phase shift wave plates called quarter wave plates and half wave plates. So a quarter wave plate will rotate circularly polarized light into a linearly polarized state. So then you can put it through a linear filter and detect the circular polarization. And then a half wave plate can be used to rotate the state of the linear polarization. So with a combination of wave plates and then filters or analyzers, so there's 2 kinds of analyzers, then you can measure all of these intensities. So this is where I get outside of my comfort zone, because I'm kind of new to the optical, but I'm quite interested in learning more about this, actually. So the analyzers, most of us have maybe already encountered a polarizing filter like Polaroid. I think Polaroid is what's used in sunglasses, for example, to make vertically polarized filters. So again, with the analyzer, after you've taken your light and put it through a modulator, which allows you to make these different polarization states that you want to measure, you need to put it through an analyzer, which again narrows down the range of polarizations that you're measuring. So there's the single beam type, which allows only one polarization to get through. The other one is strongly absorbed. So that's called optical dichroism. It just means that one of the polarizations is allowed through and the other one is stopped. Another way to analyze the polarization of light is with a birefringent crystal, so if you have unpolarized light coming into some birefringent material, it gets split into orthogonally polarized modes, one called the extraordinary ray and one called the ordinary ray. Here the extraordinary ray is vertically polarized and the ordinary ray is horizontally polarized. You might have seen this before by putting a piece of calcite over text, you get a double image. Those two images are 100% polarized light in orthogonal polarizations, but our eyes are insensitive, so we don't detect the polarization. So this is nice. When you have a crystal, you can measure, you would get a double image. Like, for example, if you're looking at a field of some stars, each of your stars would become 2 points of light, and you can measure the intensities of those 2 points of light and do simultaneous measurement of 2 orthogonal polarizations. But in a crowded field, that would become difficult because you'd have overlapping dots from different stars, and then maybe doing something with a Polaroid filter would work better. For example, you could use a Polaroid filter for an extended body, like images of the moon or of an asteroid and things like that. In radio, yeah?
I was just going to say some of the optical, I guess you'd call it photometry, they actually use fibre optics so that they just isolate one star and then analyse that light. Can something similar to that be used for this kind of work?
You could do something like that, yeah. If you had a bunch of fibre optics on each of the stars that you wanted to image, and then at the end of those fibers, you put your crystal to split each one into 2, yeah, then you'd have a lot more control over where those dots end up. In radio, this is actually quite a bit simpler. In radio, if you want to measure both polarizations, you just put 2 dipoles across. One becomes your X dipole, and the other one becomes your Y dipole. And then you just measure the voltages on those 2. And by taking different products of those voltages, you can measure all 4 Stokes parameters pretty much simultaneously. This is the way it would look for kind of your classic dipole antenna. Even on the more fancy feed horns that are put on the bigger telescopes, you have, here's your feed horn where all the radiation is being focused and channeled into this waveguide in the back, and then there's some fancy waveguide technology that splits the 2 polarizations, and one comes out along one waveguide and the other one comes out along the other waveguide. So that gets called an orthomode transducer. Just means transduces means it pretty much transmits the signal, and orthomode means orthogonally polarized modes or natural modes. Excuse me. So I'm going to take a moment now, switch gears. Now that I've talked about all these different magnetic fields and ways of measuring polarization, I'd like to talk a little bit about the strongest magnetic fields in the known universe. And none of my talks would be complete without including an animation of Pulsar. So here you see the neutron stars swinging around, and those green lines represent the magnetic field of the neutron star. And we have these beams of emission coming out of the north and south poles of that magnetic field. When you spin a magnetic field, it emits something called dipole radiation at the frequency of its rotation. So you can kind of think of it as a way of converting magnetic energy into electromagnetic radiation. And actually, it's converting, in the case of pulsars, it's converting the spin energy of the neutron star into electromagnetic radiation. So if we look at the pulsar population. Every one of these dots is a pulsar in our galaxy, and they're being mapped on this diagram. It's called the p dot diagram. And so on the x-axis, you have spin period, and this is logarithmic. So this is a spin period of 1 millisecond, 10 milliseconds, 100 milliseconds, 1 second, and 10 seconds. So there's quite a large range in spin periods. And then on the x-axis is the spin period derivative. So this is talking about how quickly is the spin period changing as a function of time. So in the case of the period, an increasing period means the pulsar is slowing down. So the higher up on this diagram, the more quickly the pulsar is slowing down. And up in the top right-hand corner, well, there's maybe before I introduce that corner, I'll introduce the lines that are going across. Using, I guess, some pretty basic assumptions about how heavy is a neutron star and what's its moment of inertia, which is really talking about what is its resistance to slowing down. How good a flywheel is that neutron star? You can infer things about the strength of the magnetic field that's slowing it down. So here you see a line that's labeled 10 to the power of 8 Gauss. So a Gauss, there are 10 to the 4 Gauss in a Tesla, if you're more used to thinking about magnetic fields in Teslas. So this would be 10 to the 4 Teslas. And here you see a line 10 to the 10 Gauss, so that'd be like 1 million Teslas. And then 10 to the 12 Gauss is this line running through here. That's kind of your average run-of-the-mill pulsar. And then you have these ones up here that, just from the spin down alone, we can infer they have a magnetic field of the order 10 to the 14 Gauss. 10 to the 14 Gauss is 10 to the 10 Teslas. That special population of pulsars that I've put, sorry, they're not all pulsars, they're neutron stars. If you look at the symbols down here, we've got a combination of neutron stars that emit mostly X-rays and gamma rays, like these open ones down here, and neutron stars that are identified as magnetars. These magnetars are the ones that are thought to be powered, their emission is powered pretty much by all of the energy in their magnetic field. They would emit all the high energy particles, and all the high energy emission that comes off of them would continue to come off of them even if they weren't spinning. So their magnetic fields are so strong, they're above something called the quantum critical field, or also known as the Schwinger limit. It's given by this equation here. So here you have the mass of the electron squared, the speed of light squared, the charge of the electron, and then Planck's constant. So from all of these things, you can put this together and say it's around 4.4 times 10 to the 9 Teslas. But here we're talking about 10 to the 10 Teslas, so we're above this quantum critical field. So what is this quantum critical field? Well, in quantum electrodynamics, when you get magnetic fields above a certain limit, or even electric fields above a certain limit, Maxwell's equations pretty much break down. So everything that we know about waves and the superposition of waves just adding together, all those things start to become nonlinear, and it's thought that the energy density in this magnetic field is enough that it starts to spontaneously produce matter-antimatter plasma of electrons and protons. They're called virtual particles, but these virtual particles modify the behavior of the vacuum. So you get this thing called vacuum birefringence. So the vacuum no longer behaves like a vacuum. It acts like a birefringent material, like a calcite crystal. This is kind of neat. So people have actually been able to measure this vacuum polarization or vacuum birefringence from a magnetar by looking at the optical light. So the idea is that if there was no vacuum birefringence, looking at this magnetar, you'd have electric field vectors oscillating in radial directions, and then integrated over the whole neutron star, you would get a net zero polarization. So it would depolarize the signal. But if you include the effect of vacuum polarization, it aligns all of the electric field vectors in a certain way. So you will get a linearly polarized degree of linear polarization in the image of this magnetar. And this has been detected, and it's been held up as the kind of first evidence of this quantum electrodynamic effect, which sounds pretty far out. So magnetic fields are amazing, and polarization is pretty much the only way to detect magnetic fields in certain situations. I'm going to end the talk on a somewhat unconventional note with a picture of a dung beetle, partially because the ball reminded me of a neutron star, but also while I was searching for news or interesting pictures to do with polarization, I read dung beetles actually navigate. They can walk in a straight line while pushing a ball of dung by using the polarization of reflected moonlight. And so some people who were studying dung beetles noticed that they make straight paths only when the moon is out. And they weren't sure if they were looking at the moon and using that as a beacon, so they did a test where they made sure the dung beetle couldn't see the moon, and then they put a polarizing filter over it and found that they could steer the dung beetle. So this tiny little insect is somehow able to detect polarized light, which is pretty amazing. I'll end there. Thank you.
Have you got any questions for Willem? I've nothing down about you.
I seem to recall there was a big result from the BICEP telescope in Antarctica about gravitational wave detection based on polarization.
Yeah.
And that turned out to be dust.
Yeah.
So the question is, how do you make sure your data is real when you're looking at polarization and not an artifact of dust, for example?
You have to be pretty careful, and I think some results are a little more tenuous than others. Even some of those pictures where we see these really nice lines drawn, those lines aren't actually the way they're imaged. That's a model of the magnetic field put on top of the brightness pattern that we see from the black hole, for example. And that model of the magnetic field comes from the linear polarization. But if you plotted just the linear polarization with a few little ticks, it wouldn't look quite as interesting. So there is a little bit of artistic license taken in some of these images. But in saying that, I shouldn't be too disparaging. The models, trying to model the observed polarization in that case, for example, isn't possible if you removed magnetic fields from the physical model. So in that sense, at least for the black hole image, they're quite confident in the presence of the magnetic field. The BICEP2 result is difficult. The effect that they were trying to measure is very challenging and notoriously difficult, and easily corrupted by foreground fields. So I think they're trying to measure this, I think it's called the B mode of the cosmic microwave background emission. So there's different ways. It's again via scattering of light. In this case, it's called Thomson scattering, where the radio photons from the cosmic microwave background scatter off of free electrons. And there's two different ways that produces a polarized signal. One is fairly easy to detect. The other one, the B modes, are really hard to detect. And I think when you start getting into that hard to detect regime with all these confusing foregrounds, then you have to be a lot more careful. Yeah. I don't know if that answers your question.
I've got a question related to that. What is the B mode polarization? Is that a combination of circular and linear, or what is it exactly?
So the E mode and B mode, they're named in analogously to how we think about electric fields oscillating and B modes circulating, or magnetic fields circulating around current. But I forget the actual physics of what produces the B modes. Is there anybody else? Sergey, do you? Yeah.
I remember reading that, and at the time I'd forgotten I'd meant to look up B modes, and I never got around.
Yeah, the B modes are generated by gravitational waves, but that's about all I know. Yeah.
Something I did as a kid is that you take a piece of glass and sellotape, you crisscross the glass with the sellotape, then hold a polarizing filter on one side and look through the other side. And all those crisscrosses come up as, all the little triangles come up as lots of different colours.
Oh yeah.
So
I didn't put any pictures of that here, but there are some really beautiful pictures of just clear plastic becoming a polarizing filter due to stresses in the plastic. And this is one way that engineers can actually model stresses in a structure. They'll build a clear plastic model of the structure and then image it in polarized light. So I'm guessing that it would have come from the stresses in the sellotape that caused the...
No, it comes from the thicknesses.
The thicknesses as well.
So what's the name? If I was to look for images on the internet of that, what would I search for?
Birefringence, probably. Birefringence.
Yeah. Thin film ellipsometry is a fancy word. So that they'll shine polarized light on a thin film and then look at the polarization with another detector. And I'm guessing you might find examples of that in a kind of ellipsometry if you Google search that. That's my first guess. Yeah.
One other thing, it was just one of these science releases that came out this week, and I didn't intend to follow it up. It was a group in China had been doing research into high energy cosmic rays. These are the ones that have ridiculous energy, like the energy of a served tennis ball in a single particle.
Yeah, yeah.
And they claim that they actually come from within the galaxy rather than from intergalactic space.
Yeah.
So, which I thought was interesting. So what sort of source? It would obviously be magnetic fields involved in that kind of energy, but I wonder what it could be. Would a neutron star be able to do that?
Magnetic black hole.
Pulsars are held up often as a possible source of these ultra-high energy cosmic rays, but there is a lot of debate. They point to the young pulsars and the magnetars up in the high magnetic field end, but even then I think it takes pretty special these magnetic reconnection events. So these particles wouldn't be spewing out of the pulsar at all times, but maybe if you wind up the magnetic field from a pulsar with enough tension, you can make it snap and produce these things. Yeah.
Got one question from a YouTube viewer. What are the smallest scales of magnetic fields that can be mapped with Faraday rotation measure?
Good question. If we're just using Faraday rotation, then I guess the smallest scales would be of the order 100 parsecs. Like, for example, we can measure the Faraday rotation along the line of sight to the nearest pulsars. Yeah.
Okay, no more online questions, Steve? Hang on, I've got another one here.
Somewhat unrelated, but have you been able to detect fast radio bursts with the Warkworth telescope?
We haven't at Warkworth yet, no. There's the fast radio burst topic is pretty exciting. Just in the past week, the Chime collaboration, which has been operating out of Canada, released their first catalog of, I think, more than 500 fast radio bursts, which is, it's an exciting field, but we haven't detected them at Warkworth yet.
Okay, if there's no more questions, I'd like to again thank Willem for coming along to the really fascinating talk.